binomial expansion. Notice it's plural. So can you see how we're splitting this problem into two different expansions? First of all, going to rewrite it how?
I guess we'd say all to the half.
Yes, and then?
And then you'd say 1 plus 4x to the half times 1 minus x to the minus half.
Exactly. Well done. And explore them separately.
All less of a minus. Yeah.
Just take them one by one, and then multiply the results to get roughly that.
Yeah.
So taking them in turn. How do we deal with 1 plus 4x all to the power of a half? Do you remember the formula, by the way?
For binomial expansion?
Because you don't have to, but in fact, let's call it up. But it is one that with enough practice, it's...
I do briefly remember.
Yeah. I suppose you have to keep checking until you're really sure. It's not that... Anyway, basically, which of these is it? Do you see the difference between that one and that one?
Yeah, but it's when you've got two different variables, whereas the bottom one, you've only got one random variable.
Yeah. I mean, let's not call it random, but yes. But more importantly, really, the point is we've got two different, or have we? No, okay, we have got a 1 there, which is a clue that it is this one. But even if we didn't, we could rig it so we had a 1 here, and we would have to if our n was anything except a, what kind of number is that with that n there?
Natural.
Natural number, meaning?
Meaning it can be, it's like it can be divided, it can be made by dividing two integers.
No, that's a rational number. A natural number is a positive integer.
Okay, yeah, obviously.
So only positive whole numbers, basically, for that version where you come down to earth again at the other end because you're in Pascal's triangle. This one here is like embarking along a row of Pascal's triangle that's never going to end. So you just stop whenever you want because the terms are going to get smaller and smaller, less and less significant. So all you need are, say, the first 3 terms, probably. In this case, 1, 2, 3, the first 3 terms. The constant term, the x term.
Exactly is the difference between that top one and the bottom one? When would you use the top one over the bottom one?
If you were lucky enough to have a positive integer power.
Oh, okay.
So if it's squared or cubed or, and so on.
But the bottom one only works if you've got 1 plus something?
Yes.
So you've got to rearrange to get it in that form if you don't already? Yes,
it may need rearranging. Also, x doesn't necessarily mean x, it could mean any function of x, which is confusing. I'd rather they hadn't said x here, but a different letter.
Right, okay.
Also, it only works if the power is less, The power can be anything, but it only works if the x function is not going to take values greater than 1 or less than -1. Because that's what makes these terms less and less significant. The fact that we're taking larger powers of a number less than 1. Because you know what happens to numbers less than 1 when they are raised to larger and larger powers, don't you?
Numbers larger than numbers when they're raised to numbers smaller and smaller.
No. If you've got, I mean, take a number less than 1, say a half. If you raise it, the more you raise it to, what happens? As n increases, what happens to the result?
The smaller it gets.
It gets smaller and smaller. Now that will be the case for any number less than 1. If it's 9/10 or 99/100. If you raise it to a high enough power, it'll always deplete to nothing. Which means that later terms become less and less significant, so you're allowed to use this formula. But you will be asked about that. You will be asked to tricky questions which depend on understanding that it's like with a geometric series needs to get that infinite sum that it's converging to, you need R, the common ratio, to be less than 1, don't you? Very like that. So that the terms are becoming smaller and smaller that you're adding each time. But the reward is that your power can be anything you like. Any kind of real number, which is the largest set of numbers, really, virtually. Not even, doesn't even have to be rational. You could have power of pi, but let's not. Right. But yeah, or power √2. That won't happen though. So what we're going to do is find the first 3 terms according to that formula. So it is worth learning at least this far through the formula and knowing how it carries on, in fact.
Yeah.
What's happening is you've got 1 plus nx, but bear in mind x means the x function. For example, here, our x function is
4x.
4x. And in the other one, our x function is
minus x.
Minus x. So bearing that in mind, 1 plus the power times the x function plus, and then you start to get a more complex coefficient, which is power times 1 less than the power. And here we start dividing by a factorial. So if you have to get the x cubed term, or the 4th term, you would be saying n times 1 less than n times 2 less than n over 1 times 2 times 3, and so on. That's all that's saying there. It's giving you the general impression of, you know, all of the things you have to multiply by above and below. And then it will be times the square of the x function. Not necessarily x squared, although you do want to find out how many x squared in the end.
Yeah.
But you've got that fraction times the x function. So try that now. Try remembering 1 plus nx plus n times 1 less than n over 2 times the square of the x function, and applying it here. Tell me what to write.
1 plus 2x.
Good.
Plus,
and then best not to be too flash here. Let's not do it all at once. Let's write the fraction.
Yeah, and then 1 minus, isn't it? 1.
No, it's
minus,
n.
Oh, n times.
The n here is
4x.
No, that's the x function.
Oh, half.
N is the power. Yeah.
Half times minus a half.
Yes, good.
All over
2 this far. By the way, if
time.
you're not sure where it starts, here you're dividing by 0 factorial, which is 1. Here you're dividing by 1 factorial, which is 1. That's just ridiculous, but that is how they're defined.
Mm.
And then that can reassure you that here you're starting with, well, here's where it actually means something, which is divided by 2 factorial.
Right, okay. But then you times by 4x squared.
Yes, all squared, yeah. And then let's just simplify that one there. So 2x plus how many x squared?
How many x squared? That would be minus a half. 4x squared.
Oh, bad luck. Well, I mean, tell me. You're right about the minus, by the way.
Minus a quarter divided by 2 is minus a half. Isn't it?
No.
Minus a quarter.
What happens if you cut a quarter in half? Which is like divided by 2, isn't it?
Yeah, an eighth.
Yes.
Oh, okay, I was trying to be.
So the fraction bit there comes to an 8. And then you've got the square of 4x, which is?
The square of 4x is 16x squared.
Yeah.
So it's 2x squared.
Minus 2x squared, yeah.
Minus 2x squared.
Yeah. And then you can say plus ... to indicate that you're aware that there are more terms you're ignoring. But you think they're going to become less and less significant, or in any way you've been told to ignore the later terms. And then doing the same with this one.
So we get 1
Yeah.
Plus
yeah.
Minus a half times minus 1 half x.
Yes.
Plus the fraction.
Yes, so we'll put minus a half times.
Minus half times minus 3 over 2 over 2 times minus x squared.
All right. You should say minus x all squared to indicate the brackets there. I'm sure you meant that, didn't you?
Yeah.
Good. Simplifying to?
Simplifying to 1 plus a half x plus 3 quarters divided by 2 is 3/8.
Yeah.
3 minus 3/8 x squared.
Why minus?
Because it's times by minus x squared.
Right, but that's why I.
Yeah, that's positive. Yeah, of course.
Yeah, that's why it matters.
Plus 3/8 x squared.
Plus smaller terms. Vanishingly, we hope small terms. And therefore, this, which has turned into that, becomes. What do we do next? We could say, therefore, one of them times the other equals.
Equals what we started with.
Or roughly equals, because we're going to start ignoring these later terms. So that to the power of a half times that to the power of minus a half, which is exactly equal to the original expression, isn't it? is going to be roughly equal to.
Were you meant to put the half inside the bracket?
I don't know. Oh, thank you. Is going to be roughly equal to.
Could you just say 1 plus 2x minus 2x squared times all of that times 1 plus a half x plus 3?
Yeah.
Because I mean, they're only going to keep getting smaller and smaller as well, aren't they? So
Exactly. Some of these are going to be too small to worry about as well, interestingly. We'll see them in a minute. But we're only going to bother with that, and then we're going to throw away some of that as well in a second. So what do we get?
We get 1 plus a half x plus 3/8 x squared.
Good.
Plus plus 2x.
Good.
Plus x squared.
Good.
Plus 6/8 x cubed.
More simply?
2/3. 8.
Oh, careful.
No, 3/4. 8 x cubed.
Good.
Minus 2x squared.
Yeah.
Minus x cubed. And minus 3/4 x to the 4.
Good. Can you see which ones we're going to ignore straight away?
Which ones we're going to ignore? Do you mean which ones will cancel?
Some of these we're going to ignore because they're too small. I mean, we don't actually know how large or small they are, but we've been told we only want the term that's constant, the linear term, and the square term.
Cubic
Any higher
term.
powers, we're going to assume are not worth worrying about.
So the cubic terms we could just cancel, or quadratic, yeah.
Not the quadratic as in square, but you mean quartic.
Quartic, yeah.
That's the word, isn't it? It doesn't start like quadratic, but quarts, which were 4 pints, weren't they? A quart? Can't remember.
Not sure.
Or was a quart 2 pints because it was a quarter of a gallon, which was 8 pints? Showing my age, aren't I? Right.
Then we'd be left with 1 plus 2.5x, or 5 over 2x.
Good, yeah.
Plus, yeah, minus.
Yeah.
Minus 5 over 8x squared.
Yeah. Which hopefully is what they said.
Yes.
Yeah. Right.
Good.
A student substitutes x equals a half into both sides. Now we probably won't get the point of this unless, and part C, unless we really imagine doing that.
All right.
Into both sides, notice, the student. So let's see what happens when we substitute x into the left-hand side. What do we get?
We'd get 1 plus 2 over, so 3 over 0.5 or half.
Which is?
Which is 6.
So we've got root 6.
Yeah.
So you can see how the student would have thought, fine, I'll use x equals a half. I'll put x equals a half into these values of x, and then I'll get an approximation. Incidentally, what would they get?
They probably get a too big value
Well, I don't know.
or too small. I
I'll
don't
try
know.
to. So you get 1 plus 5 halves of a half, which is what?
5/4.
Minus. What have we got there?
We've got 5/32. Minus 5/32.
I think, yes, you're right. Minus 5/32, yeah. Which doesn't look ridiculous at all. So anyway, I mean, they haven't said it would lead to disaster, but anyway, so what we've got, 32 plus 8 minus 5/32. It would just be interesting to compare later on. I don't know how wrong it'll be. So 35/32.
Yeah.
Root 6. Or it does look pretty rubbish, doesn't it? Because it's a good so much less than root 2. Well, it's probably less than root 2, isn't it?
Yeah. Yeah, probably.
Let alone root.
Must be less than root 6. I mean, root 6 has got to be more than 2, doesn't it? And that's barely more than 1.
Yeah, quite. But so you can see why they thought it was a good idea, because you do get exactly root 6 that way. In fact, they might have, put that equal to root 6 and then solved the equation and got x equals a half. So you can't blame them. But why should they know not to use x equals a half? Sorry?
Because they're not using really an accurate, it's not really an accurate expansion, is it? They chopped off 2.
Why not? No, I mean, this formula does give you a surprisingly accurate approximation, as long as you observe the rules, which is what I was saying they would test you on, understanding this afterword here. Where the condition was a bit like with the geometric series and the common ratio. Remember what we were saying?
That it's got to be more than +1. X has to be more than +1.
Do you mean less than?
No, more than 1 or less than -1.
No, other way around. What if you say mod of x or absolute value of x is less than 1? You're saying that x, the true value of x, is somewhere in between -1 and 1.
Oh yeah, that's what I meant. So x has to be smaller than 1.
Right. On the other hand, x is smaller than 1. It's a half. So what's the problem? See, this is where I was moaning about the format of the formula, where they're not explicit that x probably doesn't mean x, it means the x function.
Right.
And what was our x function
Half it.
in these? Well, here our x function was minus x. Well, that would be okay. If minus x is a half, then x is minus a half, and the absolute value is less than 1.
Yeah.
So it's okay for that denominator one, but up here our x function is
4x.
In which case that would be equal, with the student substitution, 4x would be equal to
2.
Which is too big. And so like a common ratio in a geometric series that won't converge, because the two are not going to become negligible.
I see.
by being, you know, divided by more and more each time. Or, yeah, just that. So the reason why the student should not use x equals a half is because 4x is greater than 1.
Yeah, they should only use like a quarter.
Yeah, so x equals a quarter might be fine. But it wouldn't give us an approximation to root 6, perhaps, would it? What would it give us an approximation to? If we said x equals a quarter, we'd have
2
2
over
over
3 over 2, 3 over 4.
3/4. What's 2 over 3/4?
That is 8 over 3.
Good. So you'd be getting an approximation to root of 8/3. Now, on the other hand, what's this about? If that doesn't work using x equals a quarter, and by the way, you wouldn't be allowed to use x equals a quarter because it's got to be strictly less than 1. And if you chose x equals a quarter, you would be equal to 1 here. So you've got to actually be less than 1. But anyway, it wouldn't have worked. But then there will be plenty of x values less than a quarter. But how are they going to work? We haven't tried any yet. Well, they're suggesting x equals 1 over 11. That's well less than a quarter, so that's fine. But how is that going to work? Now, they haven't asked us how it's going to work, but we might wonder. So let's have a go at that. Let's say 1 plus 4/11 over 1 minus an 11th. Can you simplify that?
Well, that will give us 15/11 over 10/11.
Good. And what does that simplify to?
That simplifies to 161 over 110.
Yeah. Why worry though? I mean, I'm not sure if what you're saying is right. I take that, but I wasn't expecting it. I was expecting you to cancel.
And then you got 15 over 10.
I mean, the 11s cancel for a start, and then you got 15 over 10, which cancels to
3 over 2.
I mean, you have learned to work with fractions now, so
yeah,
not like I need the propaganda here, but yeah, carry on learning to take advantage of all the cancelling with fractions.
Yeah.
And here's one that you might not have been aware of. You know, if you've got fraction over fraction and they both got the same denominator, you can check, and probably should check, because you don't want to take these things for granted, and you know, wishful thinking is always a danger, but those do cancel. And so you've got root of 3 over 2, which, shall we rationalize the denominator to see if it's root 6 or anything like it? Rationalize the denominator there?
How do you do that?
How do you rationalize a denominator? If you've got an irrational in a denominator, well, very often you multiply top and bottom by something convenient.
So 2.
Well, would that get rid of the irrational in the denominator? 2 root 2 is not rational. You're still irrational in your denominator. But rationalizing a denominator is often a good thing to do. It's not just sort of OCD tidying, but we do want to tidy that by rationalizing the denominator. Suggest something else to multiply by top and bottom, both.
9.
I'm going to have to suggest root 2.
Then you get 2.
And then you'll have a rational in the denominator, won't you? 2 on the bottom. And what on top? Well, root 2, root 3, you might retort.
Yeah.
Fine. But interestingly, root 2, root 3, even though you might prefer to leave it like that, it is equal to what? Also.
I don't know, 4.
Well, it's also equal to the root of what number?
6.
Yes. Ah,
Okay.
so if you substitute x equals 1/11 into there, you don't get root 6, but you do get a close relation.
But that one would actually work.
Yeah.
Yeah.
I mean, an 11th, 4/11ths is well less than 1, so we're allowed to use the formula. Okay, so we use the formula, and we get that. And then what do we do?
Then we to obtain the approximation.
You need to see the big picture here. You know, we've done a lot of maths in this question, but what was the purpose of it? To find an approximation, well, in general, to find an approximation to the root of 1 plus 4x over 1 minus x for values of x less than a quarter.
So it's all of that divided by 2.
Right, yeah. Kind of. We are, well, if we do all of that,
Yeah.
we will get a close relation. Do all of that with what value of x?
With 1/11th and then times it by 2.
Yes, so tell me what to write.
1 plus 5/22.
Good, so you were looking at the right hand side. That's what I wasn't sure. I didn't want to give it away. Well, exactly, yeah, 5/22, quite. Minus?
Minus,
I'll write it like this first, and you can start. So yes, 1 plus 5/22 minus 5 over what?
121. 5 over. It would equal 968.
Good.
Is that what you got?
Yep. Good. And then taking that as a common denominator, first of all, we've got how many on top?
We've got,
in the case of the 1 unit there,
968. 968.
Good. Yeah. And then what have we multiplied 22 by to get 968? I guess we've multiplied it by
8.
Only half of that, I think.
Or 4. Probably 4.
Oh yeah, sorry. That's not right, is it? What am I doing wrong? Yeah, we've multiplied it by more than 8, haven't we?
We've multiplied it by. Wait, no, it doesn't. Is it even a multiple?
Yeah,
Maybe it is. Yeah,
because we
maybe.
got 2 11s, and we ended up with how many 11s?
8 11s.
8 times 11 11s. In other words, 88 11s.
So 44
So 44 times 5
equals 44 times 5 is 220.
minus 5 all over 968. Is what now? 1143. But correct me if I'm wrong.
I'm not sure.
A bit rushed. Right. So finally, will we get 3 marks for that? Have we provided an approximation to root 6?
No, you've got to divide that by 2.
Careful.
Times it by 2.
Yes. What we've got is half of root 6, isn't it?
Yeah.
So timesing it by 2 by doing what to the denominator?
By halving it.
Halving the denominator. Good. What on earth is that? 450 plus 34.
180, 484.
Good. In its simplest form, is that? Oh God, do we have to find it? Well, actually, we know that that was only had 2s and 11s, didn't it? Yes. So it's still only got 2s and 11s. That's an odd number. So does it divide by 11? Clearly not. So that's that. So that is a good example of a binomial expansion question where they need you to not remember the formulae, but choose the right one. And you've got both versions in the formula book. But they will test you on understanding. We haven't talked about this, which is for that version. Never mind. But yeah, you do need to beware of this formula where x doesn't necessarily mean x, but the x function. And they'll test you on understanding whether the x function as a whole is less than 1. And then you need to see how to use it as well, which needs practice.
Yeah.
Okay.